Am I visible now, sir? Okay. Should I start now? So I'm starting now. Good evening, everyone. Good evening, everyone. I, Vanshika Agarwal, welcome you all for the workshop on machine learning and data science concepts and applications. I'm glad to tell you that this workshop is organized by Department of Computer Science of ITM University under Industry Institute Interaction Center of Excellence jointly with Nelumbus Technology, Varanasi. This workshop will go from October 3rd, that is today, till 5th of October. Here, participants will be benefited from the experts both from industry and academia through virtual interaction. With the advancement in machine learning, data science is found to be one of the most should be learned nowadays. It will help the learner to apply the algorithms on huge data. Learning of data science and machine learning will enhance the practical applicability in various fields. Well, I believe that this workshop can Vivek sir, now am I visible, ma'am?
Switch on your camera, Vanshika. You continue.
My camera is open.
Okay, fine. You can continue.
Okay, okay, ma'am. Well, As I was saying that this workshop can emerge as an golden opportunity for the learners to listen the experts from both industry and research academia and establish a path of applicability accompanied with right knowledge. I would like to also tell you that after the successful completion of the workshop, participants will be provided with the e-certificates. Now, before we start with the session, there are some few things I would like to mention to all the participants. That when the session is going on and you have any doubt or any query regarding to the session, you may please write your doubts in the selected questions in the chat box. Selected questions will be answered by our speakers. Second thing is, during this session is going on, an attendance link will be shared with you guys. So please make sure that you mark your attendance. And after the completion of the first session, we will be having a 10-minute break. I hope that all the participants have already know the already know the process of the workshop.
Good evening, one and all. On behalf of ITM University, I, Dr. Pallavi Khatri, Coordinator of Center of Excellence, Department of Computer Science, welcome all the participants, and I'm glad to inform that we are conducting this workshop under Industry Institute interaction of Center of Excellence of Computer Science Department of ITM University. In association, we have joined our hands with Nelumbus technology for successful completion of this workshop. It's a 3-day workshop on machine learning and data science. Its concepts and applications will be discussed during these 3 days. As we all know, why specifically we are conducting this workshop. We know that data science and machine learning, like the enormous data is going on the cloud, and we are creating so much of data in different formats, and we want our machines to be intelligent enough so that they can infer from that data and can actually give you some good results, right? So data science and machine learning is becoming very increasingly useful in all the areas of your life. Maybe every moment you are creating some data, and people are creating intelligent machines that can work on your data. So if I look in the near future, that is definitely data science will become an essential skill for each one of us, right? So every profession will definitely want you to understand data science, and how to handle the data is very important. So through this workshop, we are trying to give you a flavor of what data science is, and how actually machines, the software machines or hardware machines, how do they use this data and give you some good results, so as to maybe increase your business, or to infer something, or maybe some research or everything, so in all fields of life, right? So during this workshop of 3 days workshops, we'll be conducting 4 different sessions, which will be briefing you or introducing you to the field, right? And I know many students who are from school or freshly joined their degree programs will be very curious about learning these technology, right? So on day one, that is today, we have two sessions, that is from 4 to 5 and 5 to 6. During 4 to 5, the session will be conducted by Dr. Kshitij Sharma. He's from Norwegian University of Science and Technology, and he'll be giving you a brief introduction on machine learning. Second session, that is from 5 to 6 today, will be conducted by Mr. Mayank Jha. He is data scientist in Srijan Technologies, and he'll be talking about exploratory data analysis. Tomorrow, that is day 2, from 4 to 5, Dr. Pallavi Chauhan, professor from DY Patil University, Navi Mumbai, she'll be giving you how to visualize it. She'll be taking a session on visualization of data using R programming. And from 5 to 6, Mr. Sumit Srivastava from University of Twente, Netherlands, will be talking on uncertainty in AI, right? Day 3 will be a panel discussion in which your queries will be resolved. Some discussion will be done on that day. And that panel discussion will be facilitated by Mr. Gaurav Sharma. He is a senior research engineer at American Express. So this is about the sessions, and this workshop, definitely when we started, we never thought of that this would get such a huge response. Nearly 800 participants from all over the country have registered for the course, and as I can see, approximately 300 of them are online attending this session currently, and we are expecting more to join. And only one thing that brought you all together on a single platform is your interest to learn data science and how a machine learns, right? So I again welcome you all, and I wish that this particular 3 days will be a successful venture that we have created, a successful workshop will definitely benefit you in some manner, that you create your interest to data science and machine learning. That's all from my end. I wish you a successful completion of the workshop. Thank you everyone. And now Vanshika will take over. Vanshika, are you there?
Yes, ma'am. Yes. Thank you, ma'am. Thank you so much. So now I would like to welcome our speaker of the day, Mr. Kshitij Sharma. So our first speaker, Mr. Kshitij Sharma, will be giving this session on machine learning, a brief introduction. Kshitij is a senior researcher at ISSE NTNU. He has a PhD in computer science from EPFL, Switzerland. During his PhD thesis and as postdoctoral researcher at EPFL, Sharma sir contributed towards learning analytics methods, MMLA, and applied statistics and machine learning. His research interests are using multimodal eye tracking dialogues, user actions, EEG, facial data, using empirical data to understand the learning, both individual and collaborative, to design feedback tools to learning. Sharma sir has co authored more than 85 manuscripts published in top tier peer reviewed journals and conferences. Sharma sir is an expert in applied artificial intelligence and machine learning. He has received Best Paper Award in EC Tel and had been nominated for Best Paper Candidate on several occasions. He has over 10 years of experience with projects on eye tracking, EEG, MMLA, and collaborative problem solving. Sharma sir has worked in several research projects funded by Swiss NSF. Sharma sir is also a recipient of ERCIM European Research Council Fellowship. He is also an advisor in Nelumbus Educare. Now I may request sir to please start with your session.
Sure. Thank you. Thank you so much for having me here. Good afternoon, everyone. And let's get started without any further delays. Is it, can you see my screen? Just, okay. Let's start. So, um, so thank you for having me here. Good evening, everyone. And today's topic is about giving you a quick summary of what machine learning is. And for those who want to learn more, I will provide some of the um, extra learning materials, because it's very difficult to um, cover everything in 1 hour, as you might understand. So let's start with some basic questions, right? Like, what is machine learning? So my favorite answer to that is this Venn diagram that I say that machine learning is a combination of data, features, and algorithms. And when we talk about data science, we are mostly talking about how we can use different data sets and extract features from them. When we are talking about data mining, we are mostly talking about getting information out of the data directly. And when we are talking about classical programming, what we learn in the basic first few years of our bachelor's, um, and last few years of our high schools in some cases, is basically how we deal with features. So whatever we get from the data, and how we can optimize some of the routines. And when we combine all these three fields, so machine learning is mostly at confluence of data science, data mining, and classical programming. You need to be well versed in all three of those aspects of data, coming from your sources, from your systems. These systems can be anything. These systems can be a social network. This system can be a nuclear power plant. This system can be a student himself. Like now, when you will go and you are providing a lot of data to the university by default. You are providing your demographics. Sometimes when there are video-based learning scenarios, you are providing a lot of navigation patterns to university. You are continuously providing data to Facebook, Instagram, Twitter, and whatever social network sites are there. So we live in a world where we are data providers, data and data consumers, and some of us are data scientists as well. So let's go and see, why do we need machine learning. So what is so important about machine learning that is becoming more and bigger and bigger buzzword these days? So the idea is that machine learning is the future. And I'm not saying it because I'm a machine learning scientist. I'm a data scientist. But also you see around yourself that there are more and more applications that require data handling in a way that can inform your decision. And that's the core of machine learning. And that is the basic difference between machine learning and artificial intelligence as well. Machine learning works with data and provides with decisions. And then there is an entity, a bigger entity, that is an artificially created agent that interacts with the environment. So what we can say that machine learning is the brain of this artificially intelligent agent. And uh, the interaction that are initiated from this AI side is driven by our machine learning algorithms. And you see applications from robotics to education to social media to genetics to power systems to business systems, everywhere. There is a very good article that I tell everybody to read, especially my students, is this. There is an article about why machine learning is future of business culture. Just Google this article. It's a very good read, very simple. You don't need any basic technical knowledge to understand why machine learning will become a future in a few years. We are already there almost. um, to give you some more examples, basically, is um, that shows that proves goes on to prove my point, is basically that using natural language processing, for example, machine learning and advanced analytics, basically, Barbie created a product called Hello Barbie, and it listens and responds to a child. So that's why they also have this in the big figure. You also have this audio surveillance in operation. And that's something else where ethics become more tricky in these certain cases, but we are not here to talk about that. We are here to talk about machine learning as itself and not ethics for now, thankfully. um, what happens is that you see a necklace around Barbie's neck, and there is a microphone. And what happens is that it records whatever the kid is saying, and it sends it to the servers. And what's happening at the server is basically the recording is being analyzed, and it determines the appropriate response from whatever the kid has said in the past. And this way, the answers to the questions such as what the favorite food of the kid is, or whatever conversation they want to have with the kid, is stored. So that's something that already we are saying artificially intelligent friends for kids. Another example is this very peculiar flavor of Coca-Cola. At least I don't know recently if this is found in India or not, but in Europe, this flavor is getting very uh, popular these days. And what happened is that Coca-Cola has a very data-driven strategy when they want to make decisions across their businesses. So what happened is that their artificial intelligence system of Coca-Cola, they determined basically what products to develop, what new flavors to come up with. And in 2017, they launched this cherry flavored Coca-Cola. And what was happening in the back end was that they were collecting some data from mixing. In Europe and US, you have these mixing, the soda mixing in machines, and they collected data what flavors users were mixing. And the biggest mixed flavor was Coca-Cola and a cherry soda. So Coca-Cola said, okay, our users like it, let's produce this cherry flavored Coca-Cola. I'm not a very big fan of this, to be honest. Um, Another thing, I might get trouble to say this, but also Heineken, which is one of the biggest producers of beer in Europe, uh, they had a program with Walmart in US. They had a program called Shop Reception, and they were saying they were just analyzing the behavior of shoppers in front of the shelves, and they were using these metrics uh, to determine what kind of packets people buy and at what locations. And that's why in some of the countries you might find this six pack of glass bottles, because customers prefer glass bottles over plastic or over tin cans. And in some other countries you might find a different packaging, a different size of packaging as well. So again, these things keep happening to businesses. When it comes to health services, for example, in China, they're not very popular these days for certain reasons, but also in China they did a brilliant thing with radiologists. So this is basically a lung, a CAT scan of a CT scan of a lung, which has the cancer, and you can see where the cancer tissues are. What's happening is that an expert doctor reads these CT scans and determines very quickly whether this patient has cancer or not. But what was happening that with fatigue, so for example, a radiologist is looking at these scans, printed scans for hours and hours, and he is human after all, and he is bound to make mistakes. But in China, what they did was very brilliant, according to me. And they said, okay, let's collect a lot of CT scans, and let's ask our experts to rate a few of them. And they collected around 1.4 billion CT scans, and they collected each year. And then they trained their machine learning algorithms to figure out whether the person has lung cancer or not. So they completely removed human intervention and errors coming out of that. This is brilliant for me. Also, you might have heard about Google's project DeepMind, which was inspired by neuroscience mostly, but also the main purpose of DeepMind is to create a machine that can mimic basically the process of our own brains. And you might be seeing articles about that it beat humans in chess. Oh, machine learning beat humans in chess a long time ago, but also there is now they are beating humans in more and more intriguing games, like strategy based games like StarCraft and things like that. Also, I'm hoping that I'm talking to a population that is millennial, and that means they have most of them will have a Netflix account, and big data analytics is helping there as well. So they are predicting with your behavior what would you like to watch more, and they are increasingly creating content that is catered for your needs only. And how can I not mention Facebook, for example? I grew up with Facebook as my main social network option. And the idea is that it can get also scary. If you are following politics in the past, there was these scary allegations on Zuckerberg that he is not dealing with his algorithms in a proper way, that no fact checking is there and you get whatever you like to see. And this is only because basically almost 2 billion people are updating their statuses almost 300,000 times per minute. That means we, as a consumer of Facebook, we are giving it a huge amount of data so that it can pinpoint us in one of its multiple categories. So these are good, scary for some people, nice things coming out of these kind of projects. So for example, this is a um, very famous structure of columns in Barcelona. Basically, it's called Sagrada Familia, and Gaudi was the architect of this structure. And what he did was he used nature as a lot of his inspirations. And um, IBM in this case, they reproduced his style basically with an AI. So it's not only business and money involved, where business and money are involved. AI is also getting progress where art and culture. I by no means I want to say that art and culture has no money, but also in more recreational activities, big data and machine learning systems are showing their worth. Also, there are a few funny examples in this case. So for example, this is a photo of Asian descent, but a New Zealand resident. And AI AI said that this is a fake photo because the eyes are closed. So in this case, this was a big case because the AI was deemed to be racist. So now we are going again in the ethics, but I see it as a very funny yet alarming situation. But another thing that Microsoft trained its its um, its bot, basically its chatbot on Twitter data, and it turns out to be anti-feminist and pro-Hitler. So these kind of things are called biases in machine learning, and these biases, we have to be very careful about these biases, because whatever we are training our algorithms with will go into the decision-making process. So for example, we see that there is a lot of hate speech on Twitter these days, and Twitter is doing a very good job to control it. But still, when things go out of proportion, out of hands, you see a lot of um, hate posts on Twitter. And when you train your algorithm according to that, the decision making will be according to that. Same is for this poor guy who with his all open eyes, was deemed that his eyes were closed, because the population of New Zealand is not predominantly Asian, of Asian descent. They think that people with small eyes don't exist. So this is again a big bias, and this will come in one of the panel discussions, I'm sure, that how these biases can be removed. Another hilarious example for me, but again alarming example, was that Amazon, when you submit your application to Amazon for technical jobs, basically your application goes through an AI, and since it was trained on previous successful candidates, and most of them were male candidates, it turned out that it was anti-female, because one of the things that he learned, the bot learned, was that all the successful candidates, most of the successful candidates were male. So as soon as he was the bot was looking at gender female, the candidate was already getting some negative points. So these are the things that we should be careful about while training our machine learning algorithms. Now, the thing is, we have talked for almost 15 minutes about what is machine learning and why it is important and what are the some biases. But now, how we process, how do we get from data to decision? And that is what I will tell you in remainder of this talk. um, so there are two broad categorization of machine learning algorithms: supervised and unsupervised. I always tell, one of my favorite analogies for my students is that training a machine learning algorithm is like teaching a kid. So in supervised algorithm, what you do, you take a picture of a bicycle and you take a picture of a banana, and you show it to a kid and say, hey, look, this is a bicycle. This object on this image is called bicycle. Take a picture of banana. Tell the kid that the picture is of a banana, and repeat this process 10 times, 20 times, or more. And then you start testing the kid. So you show him a different kind of bike and ask, what is it? In that case, you tell the answer. So you start giving some worked out examples and then you test. And in that case, you also start punishing the negative answer. So you do some sort of negative marking. In unsupervised, there is no teacher for the kid. So the kid is looking at pictures, tons of pictures of bicycles, tons of pictures of bananas, and trying to group them in separate categories by himself. So maybe he will learn that, oh, look, bananas are yellow or green mostly. So okay, whatever is yellow and green, I will put in the banana category, or category X. I don't know, the kid might call banana pumpkin, because we don't know what to call it, right? So today we will see how these one of each, for example, how one supervised algorithm and one how unsupervised algorithm works. If we have sufficient times, I will go to unsupervised, but today we'll mostly focus on the supervised learning aspect, because that goes very well with the training the kid example that I just said. Now, the first step of any machine learning algorithm, or any machine learning pipeline, as I would like to say it, is you have collected your data already. So that's the first step taken care of. And then you start with extracting features from that. I will not go in too much detail, but I will just tell you, for example, what different kinds of features look like. So for example, you can have numerical features, you can have categorical features. So for example, if I'm collecting information, collecting data from a warehouse, let's say. So I have some items, I have their weights, I have their outlet locations, I have their supply types, whatever, and I have their prices. So based on these kind of things, we can start categorizing them into numerical or categorical. In numerical, we can have the weight as continuous, but also we can have their price as discrete, because you cannot go below cents or below paisa in old ages, actually. But okay, you have certain description, and you have some segments. Some variables are for product description, some variable are for store description, and usually people don't do that, but I suggest them to see how what are their impact, basically. So for example, if my target is to predict outlet sales, does identifier have a good high impact? Maybe no, because item ID does not make sense unless you are selling two products and one is selling high and one is selling low. Then item ID is a very good feature. But maybe weight has some features, visibility has some other impact which is high. If one item is very famous, it's very likely that people will buy it. But let's not go in this direction any further. And let's say that once you have collected your data, you have extracted some features, and these number of features, here you see almost 10 features on this slide, but this is a very basic example and very um, tailored example for classrooms. In real world, you will see that you can go, these features can go very easily from a few tens to few hundreds to few millions very easily. Like these things go out of hand very easily. um, sorry sorry about that. Okay, let's continue. So as I was saying, that these kind of things um, can go out of proportions very easily. So you need some sort of feature space reduction. So what is feature space is basically the space that is created by collecting all these data and extracting the features from this data set. So once it goes out of proportion, you need to reduce these kind of you need to reduce this space, because um, forget about handling millions of dimensions. We can't even think properly out of 21 dimensions, right? Like if you're well versed in string theory, you can still think in terms of 21 dimensions, but you can only visualize 3 at most. So that's the problem, and that's why we need to reduce the feature space, and we'll see a few techniques today. But why does it matter? So because one thing is space. We have limited space to store data, right? And when it comes to number of features, the more the features, the more the number of features are, the higher the space requirement. And also less features also lead to less computational and training time. So the less number of features you need a kid to say that look, there is a bicycle, it has 2 tires, 2 wheels, 1 handle, some gears, and you're good to go. But if you start telling that, hey, look, this pixel is blue, this pixel is red, then the kid will get confused as well. And also with more information about machine learning algorithms, you will also see that some of the algorithms, they do not perform very well when they have a large number of features. So it also helps in their efficiency to reduce these features. The first thing that feature space reduction you can do is basically take away the multicollinearity. So for example, that means multicollinear features are those that are highly correlated with each other. For example, you have 2 features, time spent on treadmill in terms of minutes and calories burnt. So if you run for longer periods on treadmill, you will have more calories burnt. So these are highly correlated to each other. So you can keep only one of them in your algorithm. You can remove other, because it doesn't make a sense to keep both of those features. And also, as I said, we can think in terms of 21 dimensions, but also we can only visualize only 2 or 3 dimensions in 2 or 3 dimensions. So because 4th dimension is not possible to plot. A few tricks. So for example, sometimes you don't have complete information about all the examples that you're collecting. In that case, you can remove the columns that have too many missing values. So for example, in certain cases, you might not have age of all your participants. So you can just remove age altogether. Also, you can just count the number of missing values in all the columns and simply say, okay, if my count is more than, let's say, half of my examples, so if half of my examples don't have that particular feature, then I remove that feature altogether. Also, if one of the columns or certain columns have low variance, that means they don't change much. So if they don't change much, that means they don't have enough information to give me any decision. So let's say I go out, if it's sunny, I go out for a run. If it's windy, I go out for a run. If it's rainy, I go out for a run. If it's snowing, I go out for a run. That means whatever is the weather condition, I'm going out for a run. That means weather condition does not carry enough information about my decision of going out for a run or not. So that means there is not much variance to be computed in that case. And of course, variance is range dependent, so you have to be a bit careful, because if there is a value that is between 0 and 1, the variance is smaller than if the value is between 0 and 1000. So normalization is very important in this case. So you normalize everything to one range, which is 0 to 100, 0 to 1, you choose, but keep everything in that range so that the low variance filter works. Then we started by looking at high correlation filter with the multicollinearity, and this is something that is very important, that you visualize the data, as you will see in this course already. And one of the visualizations that you can do is this scoregram or correlation plot. And the idea here is that the darker the color is between two variables, the higher the correlation between them. And now you can start removing all the correlations that are below certain threshold, both on positive and negative side. So for example, we can see that, let's say, I don't know, qualification of working age adults and drug-related hospital discharge are very correlated to each other in this case. So you can remove one of them for certain purposes. Another important aspect of feature, another important algorithm for feature space reduction, or as we call it, dimensionality reduction, is principal component analysis. So what's happening here, I'll just give you a quick overview of PCA, and then we'll see how it's implemented. So let's say that there are certain data points that we collected, and we put them on two axes, and we see that along the diagonal, so along the diagonal they are varying the most, so the most maximum variation is along this arrow. And we also see that on the perpendicular side, which is, these two are not the axes, these two are not the data that we collected, but there is a little bit less variance on the perpendicular axis. So what PCA essentially does, it just rotates our space in a way that we don't have to, that one axis is the maximum variance, the second axis is the second maximum variance, and if there are more dimensions to the data, the new axes, or as we call them, principal components, they are sorted in order of their decreasing variance. So in this case, for example, the horizontal principal component has the highest variance in the data, the vertical principal components has the lowest variance in the data, because there are only two dimensional data in this case. And this is what principal component does. And then you can basically, what you have to do from here, you rotate and make these, make these your new dimensions. And that's what principal component does, analysis does. And let's see a quick working example in R about how it works. Okay, so let's see. So this is my basic RStudio workbench, how it looks like. And what I'm going to say is that I will need some data to reduce. And if I try to do, so iris is basically data of some petals, and it has these four features, let's say. So how the petal width and length are, and how sepal length and width are, and there are three species that we will be distinguishing today, let's say. And as you can see, their ranges are quite different. So for example, one is between 0 and 2.5, one is between 1 and 6.9, one is between 2 and 4.4. So basically, we will at some point of time do some normalization here as well. Then let's quickly add two libraries here, which are my favorite two libraries when it comes to plotting. And ggplot is my favorite because it basically, when you will learn about visualization, you will learn that it's very important to keep the data separate from the visualization. And what we are going to do, we are going to just plot all the um, first, to see how the data looks like, we will just quickly plot everything. So let me just copy paste here to save some time. So X is sepal length and Y is, let's say, sepal width. And what we want is our color to look like whatever species we are plotting, right? So this is the data, and the plotting layer is basically, we call jitter plot, because I don't like the over plotting. And then we keep a nice black and white theme like old cases. And to say that to have just all the legends on top. Okay, so here is our data in terms of first two features, and you can see that there are 3 species, and they are a little bit so you can clearly see that the red is very distinguishable from blue and green here, and it is a bit problematic because, of course, we don't see that. And now let's quickly copy paste some stuff and say how the data looks like when we visualize it with everything that we have. So we need petal length here. We need petal width here. Then we need petal length again here, and petal width here and here. So these are all the 6 combinations that we have. And to be precise, we just call them by names so that we can have them in one big plot. Of course, we need different names. Sorry for my dirty programming here. And then in the end, I'm just going to say grid arrange. So this is how you can arrange different plots in one big, beautiful grid. So P1, P2. And we want everything in 2 rows. And let's see. Oh, sorry. Of course, I haven't made them. And so here is the result. It will, oh yeah, perfect. So now this is the data when it's seen from 4 different dimensions, and you can already see that even plotting 4 dimensions gives me hard time because we are looking at 6 2D plots here, and that's why we need to reduce already the feature space. And here you can see that red is pretty segregated, but blue and green are not that segregated. So let's see how we can start looking at some of the PCA methods and plotting. So this is just the data now. And now, because R is such a wonderful tool, I'm just going to quickly say that I want a dev tool library because I want to install some packets from GitHub. So install GitHub, and here I just want to include one very nice plotting, and then of course I have to say that this ggbyplot be included. Okay, let's see. So of course it is installed on my computer, so it will not install again, but we will use a very simple function. So PCA mod. So basically PCA model, and one very simple function from R, which is called prcomp, so principal component analysis. and then we say what data we need to give it to. So basically we just need to give the first 4 columns. So here you can see that iris has 5 columns, and we don't need to give species into PCA because we are only reducing the dimensionality of features here. And so it just computed my principal component. And let's see how they look like. So this is what you see here in the plot is the 4-dimensional data set that we have. And then let's see how it looks like when I say that GG by plot my PCA, and do group by species here. All right, and for example, I will just stop some things from plotting here, and I can't work without my favorite theme. Okay, so this is how the data looks like with the first 2 standardized principal components. So here on the x-axis, we can see that the first principal component already explains 92% of the explained variance in the data, and the second one already explains the remaining 5%. So it's always the remaining 5%. So that means if you combine these two, you're already explaining almost 98% of the variance in the data. So whatever variance was in this plot has 98% of that. We can see how others have worked. So all we need to do is to say that choices here is 2, 3, or 3, 4. We can just go directly to the next 2 principal components, because it would have computed 4 principal components given we had 4-dimensional data. And you can see that the principal component 3 and principal component 4 combined explain the remaining 2.2% of the variance, because whatever PCA computes is exactly the same amount of variance. But in this case, we can already see that with only 2 new dimensions, which we are calling principal components here, you can explain 98% of the data. And if we want to see also that where the original dimensions are, we just have to say that this needs to be true. And we can already see that the petal width and petal length are very correlated. The correlation is almost 1, and this is 0 and 0 in the middle. And here we can see that, for example, petal width and petal length are highly correlated with the first principal component, and there is a small correlation with sepal length as well. But sepal width and sepal length are also quite orthogonal to each other. And now we can already see, let's go back to this figure, and we can already see that these 3 groups are easily distinguishable. Just by putting a simple lines, we will reduce a lot of error. So from this 4-dimensional data, this 4-dimensional data, which had the 100% variance, where we could only clearly distinguish the red class or the red species, here we can already distinguish all 3 of them very easily, and with 2 new variables only. And that's about PCA. So and you can also start grouping them in certain. So I will not plot the variance here, but I just want to say that, hey, give me some plotting ellipse. So we can see that already we can see that they are quite distinguishable, and this is the normal plot. So you can also get some uncategorized values here. Okay, let's go further and see what is so you might have heard about classification and regression. So basically, when we're talking about classification, we are talking about we are essentially talking about putting data into 2 categories. And when we are talking about regression, we are talking about predicting a value. So classification is for discrete target and regression is for continuous target, when we have to predict a value or versus we have to predict a category. So let's quickly see how a basic classification algorithm works. So this is what we call the centroid based classifier. So let's see, we have two classes, red and green. And so the first step is to compute the centroids of these classes. So we have the red circle and the green circle there. If then a decision instance comes, that means there is a new data point that we need to classify. And then what we do, we compute the distance from the two centers, red and green, and we just assign the class. So for example, in this case, the green centroid is closer to the red to the new data that has arrived, and we compute, we give it a green label. Now, another thing that we can do is not compute the distance from the centroid, but we compute distance from all the points in the data, and then we see which are the nearest neighbors. So that's why it's called nearest neighbors algorithm, or k nearest neighbor. When you say, okay, I will vote between closest 3 data points here, and again it will go into the green category. In terms of regression, when we talk about predicting a value, so here we were predicting a class, so red class or green class, star class or triangle class. But when it comes to predicting a value and a continuous value, so for example, here what we want to predict is how much money we have spent on ads in $1 million and how much sales we are making, again, $1 million. And we see a very beautiful plot here. And the model that comes out is basically for every million you spend, you get by default, you get by default 88 millions in your sale, but for every million you spend on ads, you get 14.8 million extra. So that is a simple regression, simple line, y equals to mx plus c, where m is the slope of the line, right? We have all done that in our high schools. But again, as I said, this is a very tailored data. This is a fake data that I created for this lecture. In real life, it doesn't happen. And what happens is that you get from very good fit. So we call it good fit when most of the points are on the line or very close to the line, to a decent fit where you still see that the errors are not very, the points are not very far, to a very bad fit where you just see a line, a few points, and everything around it. And this is the problem with linear regression, that when I say linear regression, that means we are by default assuming that there is a line to be fit, which might or might not be the case. And that's why, again, if you go and take the same data with some more data points, you will see that the line which was fitting very perfectly here, that means most of the points are on the line, and which are the points that are not on the line are not very far away from it. And here we see that there are only a few points. This still is a very good fit, by the way. This still gives you a good prediction, but not very accurate prediction. In some cases, you might be spending more. So for example, in the top right corner, you might be spending on your ads. You might want to spend a little bit less on your ads to get more benefit, and that means your client will fire your machine learning company. So that's why somebody invented polynomial regression. That means we are not only assuming that there is a linear relationship between money spent on ads and profit made on sales, but it could be, for example, here a quadratic regression, a quadratic relationship. So the more money you spend, not only it increases your sales linearly, but also quadratically. That means you get more and more money that back when you spend money on your ads. But all these kind of regression techniques, they have certain disadvantage here, that we are assuming certain relationship between data on x-axis and data on y-axis. The x-axis and y-axis variables, we are assuming certain relationship between those two, and we will see in a couple of minutes how we can not assume those things, because again, assumptions lead to biases, and we have seen what biases can do. But first, before we go and see some more algorithms, what we would like to know is how we can know. So how do we know that this is a very good fit? So visually, I have told you that if most of the points are on the blue line, and if those points that are not on the blue curve, sorry, are on the are close to the curve, that means it's a very good fit. But most of the times you don't see these kind of things. Most of the times you cannot even plot the data. As we saw with 4 dimensions, we were running into troubles plotting the data. Imagine if you have million dimensions, then you cannot plot the data. That means you need to go back to some sort of measurements. And we will see now how regression and classification quality is measured. So let's say here what we have is pairs of original data points and predicted data points. So basically what's happening is that this is a group of original and predicted. This is another group of original and predicted. In this case, the prediction was higher in value than the original, but you have also the other examples where you see that the original value is actually higher than the predicted values, right? So here it's this one is very close, this one is very far, but then again you already see that we can't fit a line here, so we need some sort of measurement. Also, this is wow, this is quite exact. These two are very low in error. These are very the top 3 are very high in error. So that's how we measure, right? Basically what we are doing is we are taking the difference between original and predicted. Very good. But the problem here is that in this case, for example, in this case, the error, if we are doing original minus predicted, in this case the error is positive, but in this case the error is negative if we are doing original minus predicted. And there might be a possibility that the sum of all these errors is 0. That means whatever you are predicting, it doesn't matter if it's higher or lower than the actual point, but in all it's going to be 0. That's why we have to have 1 or 2 measurements that are irrespective of this sign. So one of them is, of course, if error is original minus predicted, one of them is just to take the absolute value, or other one is to take the squared value. But then with the squared value there is a small problem that you are amplifying the error, so that means you need to add them and then take a square root, and that is what our RMSE is. So it's basically the squared difference added and taken a square root, because you don't also want to penalize your algorithm unfairly. This is about regression quality. I will skip a few slides here to go directly to classification quality. And then in classification quality, let's say you have only 2 classes, as we saw, red or green. You might have more, of course, but in that case, you have you can have correct predictions and wrong predictions, but also you predict cancer, if a person has cancer or not. And in that case, if the person had cancer and you predicted that he has cancer, that means you are in a true positive prediction. If he did not have cancer and you predicted that he did not have cancer, that means you are in true negative. And the ratio of sum of true positive and true negative to everything is called accuracy. But then there is a problem in accuracy, that you are not penalizing, you're not being fair, you're being extra nice to your algorithm, which we don't want to be. That means you are not penalizing false positive or false negative. That means false positive is that the person did not have cancer, but you said that he has cancer, and that's a problem. And these results should be penalized. Also, the other one is false negative, which might be more dangerous than false positive, because at some point of time you might know that he doesn't have cancer. But false negative, that means he had cancer and you predicted that he does not have cancer, and that is the problem. And that's why these false positives and false negatives need to be penalized by our quality metric. And that's why we have precision and recall that penalize false positives and false negatives respectively. So these two are very good measurements for oh, I see a typo here. It's not recall, it's recall. Sorry about that. Um, and accuracy is basically just the diagonal divided by everything. And this is not a very good measurement because it is not penalizing the mistakes that our measurement is, that our algorithm is doing. So a very good measurement of um, classification quality is precision and recall and a harmonic sum of them, so which is often called F1 score. So let's go and see how we start training our data set for our data set. So basically what we are doing, we will do, and we will see how this is done in R as well very quickly, is that we have certain available data. We divide it into training and testing samples. So we do not touch, once we have divided everything into training and testing samples, we do not touch the testing sample ever again. We will test in the end, towards the end. But so that means what we have, our new available data, the training data set, is now further divided into training and validation samples. So now what we are doing is basically, if we go back to the analogy of teaching a child, the training data set is where we are telling him that this is a bicycle, this is a banana. In validation, we are giving him solved examples. So if we are asking him, is it a bicycle, or what is it, basically, we are asking what is it, and if he tells a wrong answer, we are correcting him. And testing is basically the exam. So it's basically practice, worked examples, and exams. Let's quickly see two examples, how they work. First one is my favorite basic algorithm, which is Bayes, which works on Bayesian statistics. And let's go directly to, so what it does basically is, if I have to say that given the data set, given my data set, what is the probability of belonging it in a class? And if you apply Bayesian principle to it, it's basically it's the probability that a data set will belong in a class, probability of that class to occur, and divided by probability of that data point to occur. I will quickly go into some of the details. So this is called, so the probability of class given the data point is called posterior probability, because we know the data and then we are determining the class. Probability of data point belonging in a class is likelihood. So basically, it is the probability of an event to occur by knowing the probability of success, of a success occurrence. So for example, we are saying what is the probability of 7 heads when you flip a coin 10 times. So that's the likelihood. This is probability of the class is basically prior probability. So when we ask what is the probability of head or tail, head when you toss a coin, which is 50%, we all know. And then this is the prior probability of predictor. When you have multiple data points, you just simply multiply their posterior, their likelihoods. I had planned to give you a working example here, but I will directly go into the implementation. Let's quickly see how it's implemented in R. So for this, I have another favorite library in R, which is called Carrot, and it has tons of machine learning algorithms implemented, and almost 250 algorithms implemented. And I really would like you to go and check out this package later. And also I will just use a small library for my purposes. And what data we are using today is basically, it is some data that was collected from India. So Pima, or I don't know actually, Indians. diabetes. So basically it collects data about people, and the idea is that you have to predict whether they had diabetes or not based on the features that you're collecting. So here is the data. It has 768 rows, observations, and of 9 variables. One of variable is the diabetes, so positive or negative in this case. And we already see that there are certain NAs here. That means that the triceps information was not available, the insulin dose was not available, and so on. So the first thing we do is basically we take this we take this data set and remove NAs. So na.amit from everything. And now we see that we are left with fewer observations, but let's see. Let's go and split the data. So something that is very important in R is setting a seed, because sometimes, not sometimes actually, most of the times you will see that these things are happening, that the algorithms are basically initialized in a random manner. And if you don't have this randomness controlled, so you can control the randomness by setting a seed, you will end up in different results. But here what we are quickly doing is saying that my training sample is from the database. I want everything to be sampled based on my diabetes class, because we also want to say that, okay, we keep both classes equally in the training list, training set, I'm sorry. So you see it took 80% of the data from both classes. And then we go train data is whatever is in this sample. Let's copy paste to save some time.
Excuse me, Shikit sir.
Yeah.
Can you please zoom out screen a bit? Is it possible to zoom out?
Zoom out?
Means zoom, like you zoom it to some bigger font size is not visible actually.
Ah, okay.
If you can zoom the screen.
Yeah, sure. I can increase the font size. Wait.
Please, thank you. Actually, code is not visible. So if you can do that.
Oh, there was, it should. Okay. Is
Thank
it
you.
is it
Thank you
visible?
so much. It's visible. It's visible. Thank
Okay, perfect. So let's do this. Let's make it a bit smaller here. So we have our training and testing samples. So we just say training sample is from training, and whatever is not training is testing, of course. Then we'll go and say our model is basically train. This is the beauty of carrot package basically, is that all I have to say is diabetes. I hope okay, I copy paste so that I don't misspell. Is basically predicted by everything else. So this is the syntax for that. And then we say what data to use. So we will use the train data. And what is our method? So the method is basically naive Bayes, so NB in that case. And we have to pass something for cross validation. So what we are trying to say is that our train control is basically train control, and our method is cross validation. So what it will do, it will take 10, because I'm going to say number equal to 10, that means it will take the 10% of the training data and keep it as a validation, and it will repeat it. Oh, sorry, it will not repeat it in this case. And let's quickly see how it works. Okay, and let's also see how the model looks like. So in this case, what we see is that there is a 77% accuracy here, and kappa is basically when you penalize for false positive and false negative. So we see that accuracy is somehow misleading, because in this case we are predicting 77% accuracy if a person had diabetes or not. Then for predictions, basically what we are going to do is just to say predict, again from caret, of course. We need to send the model, of course, and the new data, so test data. And then what we will need to do is basically need to evaluate our, so this is basically testing, and then we have to evaluate. So for evaluating, again, there is a very nice function called confusion matrix. So how confused our data is. So we will just say prediction and test data and our original values. And here we can see that out of, we have 45 negative out of negative, we have 17 positive out of positive, but we also have 9 false positives and 7 false negatives. And that means that our accuracy is basically 79%, but when we penalize our data, so the sensitivity here is basically what precision would be. So basically what we are saying is that 45 out of 54 negative cases we predicted, and so on. So I see that I'm basically running out of time. So I will quickly go and say and tell you a little bit about neural network in 2-3. So basically what we need to do is we need to see another. So the way we predicted diabetes with naive Bayes, we can do the same just by changing this model here. So just by changing this, so let's say this was our naive Bayes model, and I will just change everything here. And then we want to see the same thing. So I'll just quickly copy paste and change my method. So if I say artificial neural networks, these are basically the parents of deep networks that we keep hearing. The method needs to be changed to NNet, neural network. Everything remains the same, and let's see how it works. So basically it trains a lot of weights in itself, and then it stops after, as you can see that it stops after 100 iteration. And let's see what kind of accuracy we get. So in this case, neural network has performed a bit worse than our naive Bayes here, and we can also quickly check it here, and you can see that on both. So here the accuracy was, oh, it's a lot up. Maybe I can just do prediction ANN and prediction NB here, so it will be easier. And in this case, prediction ANN and prediction NB. Let's see. So we are taking both models. We are trying to compare. Oh, sorry, because they don't have that model, of course. So prediction ANN, prediction NB, and we see confusion matrix of ANN and confusion matrix of NB. So let's see. So we can clearly see that there are more false positives here, because what we are seeing here is the positive class is not having diabetes, which is true. Of course, I agree with my algorithm completely. And we can see that there are more false positives in neural network, and there are less false positives in naive Bayes here. Let's quickly check what if. So one trick that I can tell you to increase the accuracy of neural network is just change this cross validation. So repeated, wait, I had it here. The correct one, oh yeah, here. The repeated cross validation. That means in this case, it will change it to, so for this one, you need also repeats. So it will not only divide the whole training data set into 10% validation and 90% training, but it will repeat this process 10 times. So that means it is removing some sort of bias from your data, because you might just have one kind of validation class. It will take a little longer, as you could see. So we will wait a minute, maybe. Okay, thankfully it stopped. And every time it was changing the number of weights it was training. So from 11 to 31 to 51. It basically depends how many neurons you are putting in your neural network. And now let's see again, what sort of prediction does it give? And we can already see that the number of false positives are have been reduced, but again, it was 9 in case of naive Bayes. So after all this training, we could not still beat naive Bayes. So that's the difference between naive Bayes and neural network. For smaller data sets, naive Bayes works very well. And for neural networks, you need more data. So it's more suited for bigger data sets, and naive Bayes is better suited for smaller data sets. And that's where my time ends. And I hope that you will go and see a lot of more resources. And there is this these three of my favorite resources, basically. So Andrew Hung is a professor from Stanford. He's also a co-founder of Coursera. It's a MOOC platform, open online course platform, where you can go and learn a lot about machine learning. I suggest you go there and see this book as well. And also these other two are my favorite books about machine learning, and they are very good for beginners as well. So I hope you learned something, and we can take questions if there are any. So do we have time for questions? Hello? So at this point, I can also stop sharing my screen.
Hello.
Yeah.
Am I audible, sir?
Yes.
Okay. Thank you so much, sir, for devoting your time in this informative session. So we have few queries.
Yeah.
Okay, so first question is by Wenlin Sill. She's asking, is machine learning a part of data science?
So in most of the curriculums, yes, but by definition not, because what we started talking about is that the data science is mostly it's about branding, to be very honest. So the short answer is yes. Given the current trend of branding of data science, machine learning is part of data science. But if we go by definition, actually no. Well, yes, yeah. Actually, yes. Machine learning is part of data science because it does take into data whatever information we are getting from it and some sort of decision making that is happening at the end.
Okay, thank you, sir. So, second question is from Shashank Tiwari from Unnao. He's asking, what are the applications of machine learning in electrical engineering?
Oh, that's a very good question, actually. So they are doing a lot of power. I'm a computer scientist, so I really don't have that much grasp um, on electrical engineering, but I know some things about this. When you are transferring electricity from one place to another, there is this grid management system that works at the back end. So it basically takes care of how the load is distributed from one part of the grid network to another part. And in that, this is a very concrete example. So like in grid management, there are a lot of applications of machine learning. And also they are trying to teach some things of making automated circuits.
Okay, thank you, sir. So, our third question is from Dr. Sonal Patil from GH Raisoni University, Jalgaon. She is asking, which one has a better performance, KNN or K means?
Oh, I don't think you can actually compare those two because KNN is a supervised algorithm and k-means is an unsupervised algorithm. I'm sorry that I couldn't. I had plans to talk about k-means, but I ran out of time. But so the k-means is an unsupervised algorithm. So it works better when you don't have any information about. So for example, I gave example of diabetes. If you did not have information about the patients, whether they had it or not, you have to ask your algorithm to cluster them in whatever data driven decisions you get. So it's not fair to compare k-means and knn because knn is supervised algorithm and k-means is unsupervised algorithm.
Thank you, sir. So, fourth question is from Shirang Nevargi. His question is, do machine learning holds capability to be applied in applied maths and pure maths to solve complex open problems, or can we train a machine in a way that it can do maths?
So there are I know a few projects that use that are trying to use machine learning to solve complex linear algebra equations. But we are not there yet, but I'm optimistic. And for example, there are these projects. So what you are trying to teach is basically linear algebra to a machine. Whenever you are training, you are trying to teach in advanced machine learning algorithms. You are trying to teach it some sort of differential equations. But yeah, I would say it is possible. Yes.
Thank you, sir. So, fifth question is from Yate Eseki Ronald from ITM University, Gwalior. He's asking, which is better, R or Python language?
So I grew up with R, so I wanted to say R, but now, to be honest, I would suggest with the current trends to go with Python because most of the new libraries are built in Python. So if you are new to things, I would say to learn Python than R. But R has much better visualization libraries. And also there is for most of the basic stuff, and I would say up to a certain point to some advanced stuff, you can use R for pretty much everything that you can use Python for, except some deep learning algorithms. They work in Python better because they are hardware optimized. So this is a question that I get every single time I'm teaching machine learning. So my question is the one that you feel comfortable. My answer is the one that you feel comfortable with, and also your needs. So if you are going towards deep learning and very advanced machine learning, go for Python. Otherwise you can stick to R because R is much better in basic statistics, advanced statistics as well, and some intermediate machine learning.
Thank you, sir. And so the last question of the day for you is from Hiralal Salunke from GH Raisoni Institute, Jalgaon. His question is, what is the difference between regression and classification?
So in regression, basically you are predicting a continuous value. So for example, you are predicting height of sea levels, or you're predicting weight of a person, or you're predicting some time that an event would occur. But in classification, what you're doing, you are predicting categories. So you are predicting whether it will rain or not. So yes or no kind of questions. Or regression will be how much will it rain, and classification will be whether it will rain or not. I hope that was clear.
Yes, sir. Thank you so much, sir, for answering. Um, Thank you so much, sir. Your session was very informative, and I hope that participants learned many things from you.
Yeah, sure. Thanks for having me.
Thank
And
you
all
so
the
much.
best for rest of the seminar.
Thank you. Thank you so much,
Yeah.
sir.
Bye.
So, participants, I request you to have a break of 5 minutes, not more than that, because we are already out of time. So, I request everyone to stretch yourself for 5 minutes, drink water, and be back with the next session with Mayank sir. Thank you, everyone. Am I visible, sir?
Yes, Vanshika, you can start.
Okay, thank you, ma'am. So, for our next session today, our second session for today, we have a guest speaker, Mr. Mayank Kumar Jha. Mayank sir is an data scientist at Srijan Technologies. Okay, so I would like to tell you a few things about Mayank sir. Mayank sir has an extensive knowledge in algorithm designing and implementing diverse AI and ML solutions, which includes recommendation system, image semantics, text semantics, information extraction, ML and heuristics-based image segmentation, knowledge graphs, streaming data pipelines, as well as data ops. His core expertise is architecting and developing highly optimized state of art machine learning algorithms and applications with massive scalability. I request my answer to please come forward and start the session. Before we start the session, I request all the participants to write their queries and doubts in the comment section on YouTube live comment section. Please write your queries and mention your name. Also, an attendance link will be provided you. Okay, Mayank sir, can we have you please?
Sure. Thank you very much for the introduction. So let me just share my screen. Okay, so it should be visible, right?
Yes, sir, it's visible.
So hi everyone. So I'm really glad to be here, being invited as speaker. And today's my session will be around exploratory data analysis, which in short is called as EDA. So a little about me. So I think a lot of most of the introduction it was already being given. So I'm currently working as a data scientist at Srijan Technologies, and my experience mainly lies across building ML and deep learning based applications, then deploying them over the cloud infrastructure, and then managing the scalability part, which is ML ops basically. And also, I have been extensively working on the optimization part as well for the algorithms. So let's look at the things that we are going to cover in this session. So first, I will be like giving you a walkthrough about what an EDA is. Then we will be looking at some of the important terminologies, like that we will mostly come through. We will, like, if you will start exploring the data, then you will come across these topics and you may be confused. Like you will be confusing in most of the things because they are quite new. So yeah, we will have to look at those things as well. Then after that, we will be looking at like what a descriptive statistics is all about. So we will be just looking at some simple terms, I think, which most of you are already familiar with. And after that, we will have some introduction about like what is a univariate analysis, then bivariate analysis, and some dimensionality reduction techniques, most of which are already discussed in the previous section. So I will not be going into that much detail. We will just be touching upon those things. And then I have some kind of a slide where I will be discussing about like what is the process of whenever we are bootstrapping an ML project, and like what are the process behind those things, and then that will like conclude our session. So let's get started. So what is an EDA? So before like we will get to the definition, what actually an EDA is, there are a few questions that I would like to emphasize on. So let's say like we got some data and we will be like we are yet to start with the EDA part. Then there's an always a thought that should we start using machine learning on top of that data. So the actual thing is like I see in the industry most of the times, most of the problems we are not using machine learning at all. Like most of the problems are basically, you can just solve it using some simple image processing technique or maybe some rule-based techniques. So like most of time you will not be using machine learning. That depends on the requirements, like what kind of problem you are solving. And then definitely like whether you will have the data or not. So how can we like get to know about like these things? Is this a right time to pick up ML model and get started with it, or like should we are just fine with any sort of rule-based algorithms? So there comes the EDA part. Like through EDA we can conclude these facts. We can have some solid points that yeah, this is the right time to use machine learning algorithms because we have these characteristic in our data set, and yeah, we are good to go with this data. Then there can be another problem. Like there are very like various diverse range of algorithms out there, right? There are a lot of linear models, there are a lot of non-linear models, and there are deep learning techniques and lots of things out there. So how are we going to pick a particular algorithm? Like there should be some selection criteria, right? So how can we jump upon those things? So that should be also like that will be clear once we will have a proper EDA of our data set. And another important thing that if you will like be working as a data scientist, then most of the time you will be like you will be facing these challenges. Like you will be asked with your by your manager, like what are the sort of features that has a great impact on the business. So let's say you are working as a data scientist in a credit card company, and your manager has asked that tell me what sort of features are converting more fraud detection things. Then you will have to jump upon some sort of characteristic in your features, and with the use of that you can just get back to your manager, and you can say that yeah, these are the things that heavily impact our decision making, and through these things we can say that yeah, these things are the important indicator that yeah, uh, uh, through these things we are just we can just caught the fraud detection thing. So there are a lot of nitty gritties that we will have to kind of look into our data, that we will have to be aware about before starting with the modeling phase. So that's where EDA comes in. So EDA, if I will basically like introduce you to the definition, I think now's the right time because we have some knowledge about like what sort of question that we can expect. Why is there is a need of an EDA? Then I would say that EDA is basically a kind of an art. So it's a kind of way to visualize your data, to understand your data, get familiar with it, like what sort of characteristic are inside your data. Is this like is your data really ready to kind of process through some mathematical models, or do you need some other sort of data, or those kind of things. So EDA is kind of, we can say it's a kind of big detour, right? Because there are no hard or soft steps that you can follow. And through that, you can say that, yeah, this is a proper step. And we can say that, yeah, we have our, we followed these steps and we have some information about our data. So like you will have to learn through practice, like after trying several plots, after trying several things, you will have to learn those things. So that's what an EDA is basically. So if I will like if I will show you like in a real data science world where exploratory data analysis fits in, then let's say we have like you are working for an e-commerce company, which is what here I'm showing as a reality. Then you might be collecting lots of data, right? You might be collecting user activity data. Like let's say if you are a user, you are visiting an Amazon site, right? Then there are lots of data being generated out there, right? Because whenever you are clicking some item, whenever you are making some transactions, whenever you are just browsing, there are lots of data generated with those activities, and those things are captured by the companies, right? And on top of that, where the analysis part comes in, on top of those data, you can build your models, you can make the business decisions. So there those things comes in. So the first part is like collecting those raw data. Then once we will process those raw data and we will have a clean data set, then we can do the exploratory data analysis on top of our clean data set. Now, if you will see this flow chart, so like once we will have the exploratory data analysis, once we will have the result and I would say insights from the exploratory data analysis, then only we can go to this step, like models and algorithms part, then building let's say a product out of our data, or maybe communicating or visualizing a report or dashboards, and making decisions with those dashboards. Then only we can proceed with proceed to that part. So I would say EDA is the first step if you have your clean data set. And in every data science problem, it is, I would say, not the first step in a data science problem, because obviously you will have to collect the data and then process it, then clean it and those kind of things. But yeah, one of the initial process from where your data science problem starts. So I think, yeah, like we have some good intuition about what an EDA is. Now let's look at like how EDA is majorly performed. So these are the key points that I want to elaborate on. So like there are descriptive statistics that we can use, then there are univariate and bivariate analysis, and multivariate analysis as well. So we will look at these points. And then dimensionality reduction technique, I think which was discussed in the previous session as well. So these are the things like that are majorly performed as a part of EDA. So some of the important terminologies that I want to discuss, because whenever you will be like being exposed to some data, then you will see that, yeah, these are the terms that you will come across, and it would be very much helpful for you to kind of have some previous good introduction about these things. So let's talk about features. So if you, let's say you have a CSV data set, then there can be different columns, right? And those columns are basically features. So if I would say to like what kind of characteristic those variables have. So basically we classify them into two different parts, and one of which is called as a categorical variable, and the next one is called as numerical variable. Now, of course, these are very simple terms, but my main motive is to kind of just to organize these things so that you can have a kind of good mind map, and you can relate these things whenever you will be sitting with some data and doing some work or some analysis on it. So if I will talk about like what is a categorical variable. So categorical variable are basically, it tells us about the quality of our recorded observation, right? So like we can have categories like eye color, or maybe say, let's say we have some polling data, then we can have maybe some political parties where we can just say that, yeah, political party is basically what, just a category. So that was like the categorical characteristic of a variable. And then there comes another characteristic on the basis of what we can say that, yeah, it's a numerical variable. Now, what is a numerical variable? So it basically tells us about the quantities, right? So now, of course, if we will talk about quantities, then there can be two scenarios. One where you will find that in most of the cases it will be a discrete kind of quantity, and in some cases it will be a continuous kind of quantity. So discrete is basically like a countable things, uh, something which we can count, like number of children, then defects per hour, and those kind of things. And continuous is basically like weights and voltages. We can explain these terms in a continuous terms. So just a basic simple terms. Then there's another terminology that I want to discuss. It's called missing values. So in statistics, missing values basically when we have no record for any observation. So let's say we have a CSV data set of age, weight of a person. And let's say in some row, we found out that one of the value is not there. It's just an empty. Then we describe this situation as a missing value situation. And there are in some of the data set, maybe you can have some flags as well. Like you can have some -1 or maybe NaN as a flag through which you can identify that, yeah, this is a missing value and you need to treat them. So there can be multiple things which you will have to kind of find out yourself by exploring your data, like by visualizing certain columns, by visualizing certain descriptive stats and those kind of things. So another thing is the problem comes in like how to handle this missing values. So let's say we have some certain missing values. Now the problem is like how we are going to treat it, right? So the first thing is like understand the reason. Like what could be the reason that your values are missing. And another thing could be the main thing would be to like get a better understanding of your data. Like you once you will have some good domain knowledge what a data is all about, then you can think in some wider terms, like what could be the reason that this particular value is missing. So the another like mathematical technique, if I would to discuss, then it would be called maybe an interpolation. You can use like using some related values to interpolate it to the missing values things and those things. Then there can be some ML models that you can build spatially for imputing these values. There can be some descriptive statistics that you can use to impute these values. So that depends, and you will have to try out with all these things, and you will have to see that what is working best for you, because there are no rules for this. So one of the example I would like to discuss would be, let's say we have a gender column in our CSV data set. Let's say we have a CSV data frame, and there's a gender column. And let's say we have a name column as well. So name along with the titles. Now, what if there is one column, there is one record we found out in a gender section and it's missing. So if we will be looking at, like if we will look at the name, then I think with the use of that, we can easily impute those things, right? Like if there is a Mr., if there is some name starting with Mr., then we can easily say that, yeah, then we can just impute, we should impute that value with the male category. So these are some of the things like you may found out while you will be working with some data. And this can be very helpful. So this is basically what a domain is all about. Understand your data better, and then make the imputations and necessary steps on the basis of your understanding. Then other thing is outlier that I want to discuss. So outlier is basically something which is very different from your normal observations that you have recorded. So in like whenever you will be building your model, there are some of the categories of models which are very kind of prone to failure relating to the outlier thing. Because if you are, let's say, if you will be building a linear model or some non-linear model, then those things are kind of heavily impacted by the outlier. So if you will not treat the outlier properly, then you will just mess up with your result. So that's why an outlier can cause a very serious problem, and it's really critical to kind of treat it properly and handle it properly. So now the question comes in, like how can we treat outliers? So should we drop them or should we replace them? So again, like domain plays a very important role here, because let's say we have a age category in our data set, and there's an age which having a value of let's say 330. And then we can obviously like we can have as we have a good understanding what an age of a person can be, then obviously 330 will not make any sense, right? So like that's how you can use the domain part again here. Like if you will understand your data, then you can have some of the information like, yeah, this part is not making any sense, and you can just then replace it with maybe some maximum age that a person can have, let's say 110 or 100, whatever you think, and just try out with those things and see like what is working good for you. Then another thing you can use is maybe not the maximum age of a person, maybe some mean, median age of your data. You can impute the outliers with those things. So another thing you can use can be a clipping method, which is basically substituting the 99th percentile value for your outliers. So we will be looking at like what is this percentile and those things in the upcoming slides. So the main idea here is to treat the outliers properly, because it can seriously mess up your result. And some models are really heavily dependent on these things. Then another thing is the normal distribution. I think most of you are already familiar with these concepts already, but I just wanted to kind of reiterate on that. So a normal distribution is basically a distribution where you have mean, median, and mode. All these three quantities are kind of overlapping with each other. So here in the figure, as we are seeing, we have like mean, median, and mode. All of these three things are kind of overlapped with each other. And we have a kind of symmetrical feature here. If we will look at the midline, so let me just use a pointer here. So if you will look at the midline here, then we have a proper symmetry here. If you will look at this half part and this particular half part, then we have a proper symmetry here. So that is also one of the characteristic of a normal distribution. And if you are seeing these characteristics somewhere, then you can easily conclude that, yeah, this is a normal distribution. Another beautiful characteristic of a normal distribution is like it satisfies this particular rule. So the number you are seeing here, now where does that came from? So if you will look here, so this is basically the standard deviation. This is one standard deviation, two standard deviation from the mean, and three standard deviation from the mean. So the rule says that in the first standard deviation, like when we will go left or right from the mean, in a normal distribution, one standard deviation left or right from the mean, then we will have 68.3% of our data set lying here. So that's what this rule says. Similarly, like if we will go two standard deviation left or two standard deviation right from our mean, then if our distribution will be normal, then we will have 95% of our entire population living here in this range. And similarly for this 99.97, which is three standard deviation away. So these are some of the characteristics which normal distribution has. And if you will have, if you find these things inside your data set, inside your data set distribution, then you can say that, yeah, this is a normal distribution. Now, you might have heard that like a lot of time, there are a lot of focus on normal distribution, like why it's needed, why do we need to convert our distribution to normal distribution. So the thing is, like most of the ML algorithms, they are dependent upon these things. Like if the things will be normally distributed, then once you will do the mathematical modeling through that data set, then you can have some smooth curves, smooth gradient descent, smooth learning with that distribution. That's why we always like, we always tend to kind of convert our data into a normal distribution. Then there's a term which is called as normalization. So normalization is basically nothing. In a layman terms, I can say that normalization is just converting your distribution to a normal distribution. So there are some of the methods that you can use. So I'm not going into the details of these methods, which is G-score, power transform, log transform, and min-max scaling. You can explore these things later on. You can easily find these things on the web. There are lots of articles there. But the main motive here is to kind of convert your distribution into a distribution that will be normal, so that you can have some good mathematical model with that data. So here, one of the kind of figure that I found over the internet just to make things simpler. So let's say we have this distribution. We had this distribution earlier. So if we will normalize it, Then let's say we will use some G-score normalization. Yeah, I think they have used G-score normalization here. So let's say we are using G-score transformation for this distribution, then our distribution will convert into this kind of distribution. And now if you will see here, we have some proper spread in our data, because earlier it was just a jumbled one. We had our data set all collected in just a kind of jumbled form. Now we have some spread, and we can our model can now smoothly do the gradient descents. Our learning curve will be kind of smooth, we can say that. And that's why like the normalization is very important thing that you will have, that you need to do for your data set, especially if you are using deep learning or neural nets. Then there's a batch normalization layer that you will have to, that always will benefit you. So that was for the normalization. Now we will look at the descriptive statistics. So in the descriptive statistics, basically it is just to describe your data set. So with the use of descriptive statistics, you can just have a kind of quick summary of your data set. So most of the terms we are already, I think most of you are already aware about: mean, mode, median, then standard deviation and variance, then some of the terms like skewness and kurtosis. But don't worry, we will be have a quick look at these things as well. So let's look at mean, median, and mode. So we can, like mean is simply the sum of all those things divided by number of observation. Then median is just the like sorting your data into an ascending order, then selecting the whatever the value comes in the middle. And mode is basically just based on a frequency. So that was mean, median, and modes. And let's look at some of the real life examples. So all of us are using Play Store, right? Google Play Store. So if you will, whenever we are downloading some games or some apps, we look at the ratings. Now, like have you ever been kind of you have like, did you ever think of like how those ratings were converted? So basically mean is behind the scene. Like let's say we have 5-star rating, 4-star rating, and these kind of ratings, and these were the users that gave those ratings. So and we generally see that it's showing, Play Store is showing us 3.5 or let's say 4. So these ratings are being calculated through the mean. So you can just look at this mathematical calculation that I have mentioned here, and we are getting around 3.42, which is basically, if we will round off this value, then we will get around 3.5. Then another example for the median will be like, if I would ask you like calculate the average income for our country, then in this case you will not be using mean, because mean will be pretty much kind of a spurious measure. Because if you will talk about income, then it's highly imbalanced. There are highly rich persons out there, there are highly poor persons out there. So mean will be kind of very much spurious. So in that case, you can use median. You can just sort out those incomes, and you can just select the middle one, which is a median. So just a simple term. And then for the mode, the best example could be like all of us are using YouTube. When we see like the most viewed videos on YouTube, then that is an example of mode. And let's say if I'm looking for some hotels at a particular site, and if I'm searching for some popular hotels, then that will be the example of a mode. So that was something about mean, median, and mode. Then there are variance and standard deviation, which you can use for the descriptive statistics. So variance is just simply like subtracting mean from your observation and then dividing it by and then doing the square and then dividing it by the number of observation you have. So standard deviation is basically just the square root of variance. And like I have mentioned the formulas here, and I think we have these kind of intuition from the earlier, right? But these things are used at like, these things are widely used for the descriptive statistic thing. So it's better to kind of have a kind of quick mind map of these things, so that we can think in terms of these mathematical equations. So there are some real life examples of a variance and a standard deviation could be, let's say if you are doing some customer survey, let's say you are a market researcher and you are doing some customer survey. So like you all know that customer survey are done on generally some sample of a population, right? So how can you be sure that those results that you are getting from the survey results, those are enough reliable? So in these kind of scenarios, what you can do is you can just use this variance and standard deviation. So let's say if you have a very little standard deviation, then that is a very good indicator that you can rely on your results, because there are very less noise in the decision making. Like each customer, whatever the population you selected for the customer survey, then you can easily say that, yeah, there is a very less standard deviation, and we can easily conclude that, yeah, it's highly reliable, and we can use it for the larger population. And the another example would be kind of you can use it for the outlier detection and removal purpose as well. And similarly, as like we discussed before, there was a G-score term. So in the G-score term, we also use kind of a standard deviation as a denominator. So that was some example of the standard deviation and variance. And let's talk about skewness. So skewness is basically just a measure of symmetricity of your distribution. So you can see that this distribution is kind of has a tail around right side, and this has a tail around left side. So we quantify these things as a positive skewness for this particular case, negative skewness for this particular case. So we can have skewness as a positive, zero, negative, or maybe undefined in some cases as well. And we generally use skewness and one other term that we will be looking, which is called as kurtosis, to kind of get an intuition about what kind of distribution we are having with our data set. So like this will give you basically just a single number, and with that single number, you can just, without plotting, you can have an idea like what kind of distribution, what shape of distribution you are having, and what should be the next step that you should be taking. And this is one of the example. Like here we are having a negative skewness, and skewness value of minus 1.60. And if you will look at the distribution, then we have a tail towards left, right? So it's kind of there are just less number of observations that we are having in the left side, and most of our observations are kind of on the right side. So if this will be the situation, then we can have then we will be having a negative skewness. Similarly, if there will be an opposite situation, then we will have a positive skewness. So these are just of the illustrations that I've just wanted to show, just to kind of visualize, making things simple, like how it looks like when we have a positive as well as negative skewness. So like now, if you will do some analysis for some data set and you will get some skewness value, then you can easily say that, yeah, I am getting this much positive value, and it means that this should be the distribution that my data set is something like. Some real life examples of skewness could be like people's income, and let's say number of children in a family, and maybe a number of accident claims by an insurance customer, and these kind of things. Now let's talk about people's income. So people's income, why I'm saying it has a positive skewness, because there are like how positive skewness looks like. So this is how positive skewness looks like, right? So if you will talk about people's income, then there can be a lot of population that will lie around some low to medium salary range, right? And there can be very few number of people that will be lying around a very high salary range. That's why if we are going to plot that distribution, then it will look like something look like this shape, and that's why we are saying that it has a positive skewness. Similarly for all other cases. Then we have another term, which is kurtosis, and kurtosis basically tells us about like the height and sharpness of the distribution. So we always like calculate kurtosis and relative to the normal distribution. So we generally compares it with like if it would have been a normal distribution, then what it would have been. So like there are three different types of kurtosis, which is mesokurtic, leptokurtic, and platykurtic. So these three terms, you don't need to remember these terms. So don't put kind of that much stress, like we will have to remember it anyway. But yeah, it's good to know these terms so that it will not confuse you whenever you will come across these terms. So in statistical terms, like when we will have a mesokurtic distribution, then it will look like this one. Now, if you will just recall what a normal distribution was looking like, so it's most similar to that distribution, right? So whenever we will have either, yeah, this is a leptokurtic case, or this is a platykurtic curve. And some illustrations, some figures that I have, in the case where we will be having a kind of positive kurtosis, so it will look like this one. So we will have our most of the population lying around the center of our distribution, and in that case we will be having a positive kurtosis. And if it will be flatter, like in this case, then we will have a negative kurtosis. Some examples will be like we can use kurtosis for the outlier detection, or maybe if you are planning to kind of invest something in a stocks, then to get the reliable kind of value of a sample size, you can use kurtosis for that as well. So that was all about the descriptive statistics. And let's look at the univariate analysis. So univariate analysis is basically analyzing single variable. So it is a very simple analysis from where you will generally start your analysis with. And of course, your variable could be a categorical or continuous variable. And there are some of the methods that you can use for the categorical variables and for the continuous variable. So there are lots of plots out there with for the categorical variables and for the continuous variables. So of course that will be a kind of huge session if I'm going to cover all those things. So we will be quickly looking at like count plot, which is a very simple plot, and then just a simple histogram plot, and little about a box plot. So box plot, I will be explaining that in detail little bit. And the count plot and histogram plot, that is very easier. So let's look at that. So count plot is basically, as the name suggests, it is basically a counting of how many observations we are having. Let's say we have a data set, we have a column of a gender, then this basically shows that how many number of males and females we have in our data set. Very simple. Then next one is a histogram plot. So this is we generally use for the continuous variables. And for this, you will have to decide on like what bin size you want, because first you will have to do this binning. And once you will have this bins, then you can just plot your continuous variable, and then you can have some intuition about like what your continuous variable, how the distribution looks like, and those things. Then the next one, which is very informative, I would say, is called as box plot. So box plot, it looks something like this one. So we will be having a rectangular kind of box, and there will be two tails. So one will be at the top, and then another will be at the bottom. Now this simple plot has a lot of information alone. So if you will look at, so let's start with the percentile thing. So this is basically the 20, this is basically called the Q1 range. So Q1 range is basically some just a simple range where you have 25% of distribution lying over here. Now, similarly, if we will talk about this particular line, then this basically says that if we will measure it from here, then it basically says that we have our 50% of data lying between this particular range. Similarly, for this particular line, we have 75% of our data lying between this particular range. And the range here is basically nothing. It is just a simple numerical quantity. Like if we, let's say we have a data of age, then we can have a range of age maybe from 1 to 83 or maybe 100. So that's what a range is. So minimum in that case will be 1, and maybe maximum could be, let's say if we will have an outlier, then let's say it will be 330. So, and this line is basically called as Q3. So like the percentile, as I have already explained, it is basically nothing but like how many percentage of distributions we are having between this range. And this little box, what you are seeing here, it's called as mean. So if you will have a normal distribution, then of course this mean will be overlapping with this line, right? Because what we have learned earlier, it was that in case of normal distribution, mean, median, and mode, all three of them overlaps, right? And now like we can use this box plot even for the outlier detection. Now, how are we going to use for that purpose? So if you will see here, we have something called as IQR, right? So IQR is basically interquartile range. So interquartile range is basically Q3 minus Q1. Q3 is basically this point, and this point, sorry, and Q1 is basically this point. So it is basically just the difference between the 75th value, whatever the value lying at your 75th percentile distribution, minus the value lying at 25% distribution. So if we are going to say that like something which lies beyond the 99th percentile, or maybe at the bottom of, let's say, first percentile, then we can say that we can like point it out that, okay, let's treat them as an outlier. And what you can do is you can just simply replace those values maybe with this maximum value, which is this 99th percentile. So, and let's say if it would be an age, let's say we are talking about age column, then our outlier, let's say there was an outlier and we were having an age measurement of 330, but we know that our 99th percentile of value lies maybe around 93 age. Then we can say that, okay, something which is lying beyond 93, let's treat them as an outlier. And we will say that just replace all the values beyond 93 as just 93. And that's why I was saying that replacing it with the 99th percentile value. And let's say in our case, 99th percentile value is 93. So that was little info about box plot. You can read more about this plot. There are lots and lots of articles out there. And this is, I would say, a very important plot that you should be aware of and that you should use to kind of explain your data. Now, let's compare our box plot with normal distribution. So if we will have normal distribution, then this is what our box plot will look like. So here we are not seeing mean. Well, mean will here overlapping with median. And this is like the tail will look like. Like we have a proper symmetry here. Like if you will measure this particular length and this particular length, then it will be obviously same. So that this is what it will look like in case of normal distribution. Now let's look at the bivariate analysis. So bivariate is basically nothing but analyzing two variables at same time. So basically where here we are doing just a kind of, we are determining the relationship, like how change in one variable will impact another variable. Now there are some of the techniques that we can use for the bivariate analysis. And one of them is stack plot. So let's talk it in terms of categorical and continuous variables. For categorical variables, we have a stacked plot. So stacked plot is basically you will have these bar plots. And so this is basically stacked bar plot. There are another versions for the stack plot as well. You will find it over the internet. But this is basically the kind of bar plot version for the stack plot. So here we have bars, and we have three different categories here: measles, mumps, and chickenpox, three different diseases. And this what basically shows us that for, let's say, uh, so just a second. Yeah. So let's say for the first month, let's say we have this much number of cases, then we can say that, okay, in first month, within these number of cases, we have this particular distribution for chickenpox, this particular distribution for mumps, and this for measles. And similarly, this for the another next several months. So this basically, in a single plot, you can visualize these categories, like for each of the month, what are the distribution for each of these categories in terms of number of cases. Similarly, we have a cross tables we can use for the bivariate analysis as well. So let's say we have a car data set, we have brands like BMWs, Ford, and we have colors. And if we want to visualize like how many number of particular brand in black we have. So you can just use cross tables for those kind of visualization, and it will look like something like this one. Similarly, for the continuous variable, we have a pair plots where you can just plot the pairs of scattered plots between each of the variables. So if I will say this is a petal width and the upper one is a petal length, then what we are seeing here is like this is the scatter plot between sepal length and petal width. Similarly, it will be like there will be plot between each of these variables, like one at a time. So this is basically suitable for the situation when you have just several variables, because if you will have, let's say, 100 or more than 100 variables, then that will not be feasible. So after that, I will like talk little bit about dimensionality reduction, because pretty much has been covered earlier. So dimensionality reduction is basically used most of the time for visualization purpose, and sometimes even for the mathematical modeling purpose as well. So whenever we have like we want to visualize our data set, so of course the only possible way is to have just a 2D or maybe 3D plots, right? But what if we have, let's say, more than 3-dimensional data set? Then in that case, we can use dimensionality reduction. So there are some techniques that we can use for the dimensionality reduction. So two of the techniques that I will be discussing here. There are other techniques like PCA, TSNE, and some other techniques that you may look at. And these are some of the commonly used techniques that I wanted to discuss. So low variance filter is basically just kind of calculating variance for each of the variables that you are having, and then filter it on the basis of the variance. So just you can just sort your data set based on your variance, and then you can just filter them out. Whatever will be having a little bit of kind of variance, then you can just filter them out. Then similarly, we have backward feature elimination, where you can just eliminate features using the backward selection mechanism, and where you can just select initially all the variables, and then you can just drop one by one one of them easily, and then you can just see that if there is some change in performance, then you can just either keep it or you can just throw them out. Like if it is not impacting your performance, then it means that it's not usable. Now, this is the last thing that I wanted to talk about, which is about the process of bootstrapping an ML project. So there are several parts of it, which I would like to talk about. So first part, whenever you will start with a data science problem, is ideation phase. So ideation is basically like to kind of initially start with some data science problem, like to listen to your managers, to listen to your stakeholders, like what are the problems they are facing, and then collect the ideas, research about those things. So this is what an ideation phase is. So there are a lot of process involved there. I'm not going into that much detail because we are running out of time. So the next part that is the part of the bootstrapping is the data acquisition part, where we generally collect data and we do the exploratory data analysis. And once we will have some insights about that, Then we can use like research. We can research over some facts that whether it's feasible to develop a particular solution or not. And let's say we have developed some modules, then the next part is kind of validate our modules, like are we getting the performance whatever required for the business case or not. And let's say we are just kind of satisfied with our validation score, then we can just pass it to the delivery team to just kind of launch our project. And the last thing is kind of a monitoring part where you just monitor your model, like is it performing what it was being expected of, and is it performing well or bad or not, and do we need to kind of reiterate or not. So that's how kind of ML project in a data science world works in. So that was all about, I think, and that concludes my session. So any questions?
Thank you, sir. Thank you so much for the session, sir.
Thank you.
So actually, because we are running out of time, I guess we have to skip the question answer round. We had questions, but participants are getting a bit tired, and also they were listening to you, but because we are running out of time, I guess we have to skip the question answer round.
Sure.
But
Okay.
your session was really good, sir. I was listening to your points, and I got responses personally that your session was very informative.
Thank you. Thank you very much.
Thank you so much, sir. Thank you so much for.
Thank you, Mike. Thank you so much.
Thank you. Thank you. Bye, everyone.
So I thank all our guest speakers who devoted their time for this successful session. Pallavi ma'am and the people from Nelumbus Technologies, and most importantly, our participants who gave their time to listen to us and made this session successful at all measures. Pallavi ma'am, can you say something in the end?
Um, I have nothing to say. We had wonderful sessions today. And I would like to, although Kshitij and Mayank, both of them have left, and we had wonderful sessions. Although because we had few students from very basic years or basic who did not had background of whatever was taught, so I was going through chat. So initially they faced problems, and tomorrow the session what we have conducted, like tomorrow what we are conducting is programming with R, right? So it will be a very good session where all the students, especially those who are planning to go into data science and machine learning, and already know Python. R is a very good tool. Again, you should attend that session. It will be complete hands-on session wherein you can see how exactly you are using R programming, because in today's session when Dr. Kshitij used, few of the people pointed out that it's not easy, we don't know and we're not getting anything. So tomorrow's session that will be conducted by Dr. Pallavi, Dr. Pallavi Chavan from DY Patil. So I request you to be there in the session. And tomorrow's both the sessions will be, you will love the sessions, right? So thank you all. Thank you for your patience. And thank you, Vanshika, Shivam, and Nilumbus. Thank you so much. Okay. That's all for the day. Calling off, guys. Thank you. Thank you so much.